All right, thanks a lot, Tim, for the introduction. I'm very happy to be here. So I wasn't here for the first couple of days, but if I look at the schedule, it seems like there has been a lot of talk about partially synchronous protocols. Maybe except for one talk, Dongning's talk, which spoke about Nakamoto consensus, which is in the synchronous land. So I'm going to be talking about synchronous BFT over here, and this would be on the classical style of synchronous protocols. Okay, so there has been a lot of work in this space, and I'm going to focus on one sliver of it. Okay, so let me first start off with something that you've already seen several times: partial synchrony assumption. Over here, you assume that your network is asynchronous until some unknown GST, but it is synchronous afterwards. Okay, so afterwards there is this delta bound, delta network bound that is respected. And for all protocols in the partially synchronous, protocols, when you're reasoning about safety, a key aspect necessarily is that you cannot rely on a synchrony assumption. Okay, so the canonical example that you've seen multiple times is simplex, which works in the n equals 3f plus 1 setting, where you have n parties, f Byzantine faults. You reason about safety using two core conditions. One is uniqueness within a view, which says that if you have a 2f plus 1 size certificate for any block, you cannot have a 2f plus 1 size certificate for any other block, right? And this is because honest parties vote for at most one non-mod block. Across views, a similar condition: a 2f plus 1 sized commit certificate and a 2f plus 1 sized skip certificate cannot coexist for the same view. This is because an honest party, if it sends a commit vote, it does not skip, and vice versa. If you look at PBFT, ideas are similar. Uniqueness within the view is the same. Across views, the idea is a little different from simplex. Over there it says if you have a commit certificate for some block B in some view V, this certificate will intersect with n minus f statuses that that parties have and that are received by a subsequent leader, in such a way that these two quorums will intersect in at least one honest party. Right? So a commit for B in view V implies it has 2f plus 1 votes, out of which f plus 1 must be honest, and these are the honest parties that are locked on a block on B. And in subsequent views, they are responsible for guarding the safety of B. Okay, so any subsequent leader cannot create an n minus f size status, because this n minus f intersects with this f plus 1 and at least one honest party. So this lock from one of these guard parties necessarily needs to be included by the leader in its n minus f status. So the safety arguments essentially rely on the existentiality of certificates or the non-existentiality of other certificates. Right? Skip certificate for a view implies no commit certificate in the same view. Right? And the rationale is that if that other certificate could have existed before GST, I may never know of it. Okay? If I were to abstract this, and if I were to view this n equals 3f plus 1 setting, where you have an adversary over here denoted by B of size f, okay, and let's say B is connected to the set A and the set C in such a way that the communication between them is synchronous. Over here written as instantaneous, whereas A and C have partially synchronous links between them. Okay, so if A is of size f plus 1 and C is of size f, then A union B together can make progress in the protocol. They will have these certificates, and A is well assured that C cannot make progress on its own, because another certificate cannot exist. As soon as you drop this bound from the size of A from f plus 1 to f, this no longer holds. This is your DLS lower bound, which says that it is impossible to solve Byzantine agreement under partial synchrony if f is greater than or equal to n over 3. So it very much relies on the fact that A and C cannot communicate with each other within a bounded amount of time, and that is when you have this f greater than or equal to n over 3. So on the other hand, you can ask this question: well, what if all messages had a bounded delay? What if it was the case that A and C can communicate within this bounded time? And that is the focus of this particular talk. Okay, so we're going to make a network synchrony assumption, which means that a message sent by a sender at time t will arrive at any receiver within some time t plus delta. Okay? So we are going to assume a clique where every party is connected to every other party, and there is this delta time bound delay between any two parties for any message that is sent. Okay? So think of this delay delta as a pessimistic bound. Think of it as maybe 1 second. Right? So the guarantee that you have is that your messages will reach within this 1 second. In practice, it could reach much faster. If you're communicating within just US East, this may reach within 5 or 10 milliseconds. Right? Even US East to US West, this will reach within 50 milliseconds. So these actual delays is what we are going to call the actual network delay, and I'm going to denote it by a small delta term. But this capital delta term is the pessimistic delay. Think of it as a large number, some 1 second or so. So if I were to compare synchronous protocols and partially synchronous protocols, the DLS bound essentially says with partial synchrony you cannot tolerate more than n/3 faults. With synchrony though, you can tolerate something more than n/3 depending on the exact definition that you have. You can tolerate dishonest majority, or you can tolerate up to a minority corruption. Okay? But throughout you need to keep this in mind that with synchrony you're making a stronger assumption because you're requiring every message to actually respect this delta bound. Okay? So there have been several works in this space. The literature over here is rich. There's Dolev-Strong protocol in the 1980s, there's Feldman and Micali from the 1990s, there's this Katz and Koo protocol from the 2000s. So the starting protocol that I'm going to focus on is this protocol that we worked on some 7-8 years ago. And in my opinion, this is like the simplest, cleanest synchronous protocol that one can easily understand. Okay? So for concreteness, I'm going to explain this protocol to satisfy this particular definition of Byzantine broadcast, which basically says there are n parties, f of them are Byzantine, and there is a designated sender, and the goal is to agree on the sender's value. So you have 3 properties: agreement, termination, and validity. Agreement says no two honest parties disagree. Termination says everyone outputs a value, and validity says if your sender is honest, then honest parties output the sender's value. So to recap, we have n parties. We are still in the f less than n/2 setting. Okay, we are tolerating 49% corruption, and all throughout we are going to assume that messages are digitally signed. So something that I did not mention is that to move from n/3 to a higher threshold, you need you need an additional tool, and signatures is one tool that you can use to actually go higher. Otherwise, you hit a different bound called as the FLM bound. Okay, so I'm going to construct this protocol ground up. So if you never looked at a synchronous protocol before, you should still be able to follow what I'm going to say. And as I create this protocol, I'm going to make mistakes, and hopefully you'll identify what mistakes I make. Okay, so n equals 2f plus 1 because you're tolerating f less than n/2. So to start off with, let's say n equals 3 and f equals 1. Okay, so you have a 3-party system. So each of these individual rows over here refer to 1 party each. Okay, and you have these vertical lines. They represent synchronous rounds. Okay, so the way to think about it is messages are sent in locksteps. So any message that is sent by any party in a given round at the start of a round will arrive by the end of that round. Okay, so there are ways to realize this lockstep execution if your delta delay bound holds, if you run some clock synchronization protocol. Okay, so a first simple protocol is the following. In the first round, a leader proposes a message to everyone. Okay, so we'll assume that there is one party over here that is leader 1, which everyone knows of. Okay, so leader 1 is written as a separate role. It's the same identity as party 1, but I'm just separating the role of party 1 as a replica and as the leader. Okay. So, round 1 leader proposes some value to everyone. Round 2 there is everyone votes for whatever they receive. Okay. And whenever you receive f plus 1 votes on a value, you commit the value. Okay. So, do you see any issues with this? I mean, if you don't see any issues with this, then exactly. So, I was about to say, if you don't see any issues with this, we can just go home. We have the simplest protocol ever. So, a simple thing that a leader can do is it can equivocate. It can propose a value v to party 2. It can propose a value v prime to party 3. Party 2 observes 2 votes for v and it commits v. Party 3 observes 2 votes for v prime and it commits v prime, and you have an agreement violation. Right? So, a simple update would be, okay, I wait for f plus 1 votes, and in addition I need to check that there is no equivocation. So, if that happens, then it turns out you cannot easily violate agreement, but the leader can still partially stall progress. What can a leader do? It can propose a value only to one of these parties, let's say party 3. So, it proposes this value v to party 3, sends nothing to party 2. Okay? So, party 3 receives 2 votes, one for v, one from party 3 and one from party 1, and it commits because it observes no equivocation. Party 2 receives only 1 vote from party 3, so not enough to commit. So, in this situation, party 2 has not made progress, and a typical thing you would do is just change leaders. So, a new leader will come in, and this new leader needs to know what progress has happened. The new leader will ask everyone, hey, tell me what have you potentially committed? Okay, what are the certificates of f plus 1 votes that you have? Party 3 will say, it's v, I have a certificate for v, I have committed v. Party 1 and party 2, they will not have anything. Okay? And based off of this, the leader will send the next proposal, and it will attach these status messages in its proposal itself. Okay? So, an updated protocol is you just run the status propose commit for different views. Okay? So, does this protocol work?
It's not supposed to work, but
so Itai says, by the way, Itai is a co-author on this work. Itai says it's not supposed to work, but I'm waiting to hear after the but.
So maybe some liveness problems.
So I think this protocol works. Okay, and the reason why it works is not what you think. The reason why it works is that if leader 1 is malicious, then leader 2 is bound to be honest because f equals 1. Okay, and n equals 3. And so this is some sort of an f plus 1 round protocol.
Yeah, you need to produce a message if you don't see the leader message, right?
Sorry, come again?
If you don't see the leader proposal, you have to tell this, you have to blame the leader, right?
So over here, you're not blaming. All you're saying is, in the status message, all you're sending is, whether I have a certificate of f plus 1 votes. That is all you're sending. If not, you're just saying I don't have it.
Yeah, you need the second leader to be correct.
Yes, you need the second leader to be correct. Exactly. But if the second leader is not correct, then it turns out, this cannot work, or at least as is it doesn't work. Okay. So if you generalize this, where you have 2 f plus 1 parties, where group 1 have, some f people, party 2 is a single party, and group 3 have f people, then here is exactly what a leader can do. It can make some party commit on v. Let's say party 2 commits on v. And when the new leader comes in, party 2 says, I have committed v. Group 3 say, we have committed on nothing. We have a certificate for nothing. But leader 1 prime, it comes from the same group of malicious parties. Leader 1 prime can come in and propose v prime, okay, not equal to v, and basically claim that party 2 did not send me any message. So up to f parties could be faulty, and leader 1 prime could claim that one of these party 2 in particular is malicious, and the rest of them, I can show you 2F certificates, but I did not hear anything from party 2.
So the leader in one is sending two different values?
No, the leader in one is just sending one value.
One value.
So the leader, so over here, leader is only sending one value, so so group 3 has nothing. It has votes for V, but it does not have any certificate. So party 2 does say V, but the leader just omits party 2 because it can. And it proposes V prime, and group 3 has no information to say, so they would vote for V prime, and again you have an agreement violation. So if you think through what actually happened over here is that there was one party, party 2, which committed, and that was the only party that was locked. When a view change happened, that was the only party who had this information. So what you want is that if this one party commits, you want all of the honest parties or F+1 honest parties to lock. Please go ahead.
So the point here is that the parties are not talking to everybody, it's not all to all.
Parties are talking to everybody over here. Oh, in the status message they are not. So in this particular message they are not, they are only sending it to the leader.
So what would happen if you changed it so that you were sending the status message to everyone?
So that is basically, that is one of the things that I'm going to do. You're not sending the status message to everyone, but you're introducing another round, but to achieve exactly what you're trying to ask, right? So what you want is one honest party. If it commits, you want all honest parties to lock, and that you would have if you add another round where, if I have this certificate, I'm going to share it with everyone, and I will notify everyone about this certificate. And at that point, there is party 2 who has committed, but all of the parties in group 3 and party 2 are now logged onto it because they have a certificate. And now when the next leader comes in, if you share this certificate to the next leader, the leader has to include cannot exclude all F+1 of these, because it can claim up to F of these parties did not send me a certificate, but it cannot claim F+1 of them did not send me a certificate. Okay, so this is basically the core protocol of how it works. You just keep running this in different views. Okay. And now, if I want to, I said I will solve this for Byzantine broadcast, right? And for Byzantine broadcast, you have the sender. I did not introduce where the sender is. So to connect it to Byzantine broadcast sender, all you need to do is, let the sender send its value right in the beginning to all of the parties, and then just run the core protocol in iterations, in views. Okay. So if the sender is honest, everyone will receive the same value V. And that would be the initial certificate, a special certificate about what value can be proposed. So F+1 of them would be locked on this value V, and then any subsequent leader cannot propose anything else. Okay. So let us quickly go over the key argument for safety. Please go ahead.
Are you assuming the sender is honest?
I'm not assuming the sender is honest. So with Byzantine broadcast, the requirement is that if the sender is honest, then you want to agree on the sender's value. So if the sender is honest, it will send the same value to everyone. And then you cannot propose anything else. If the sender is dishonest, if it does not send anything or if it sends equivocating values, at that point you can propose something else, but you don't have the validity condition to respect. Okay, so here's the key argument for safety. So suppose H is the first honest party to commit some value V star in some view K star. Then we'll argue two things. One, nothing else could be committed in the same view. And second, no other value could be proposed in any subsequent view. Okay, so in particular, an honest party H prime cannot commit on some equivocating V double prime. Why is this true? It's because if H prime did commit something else, then it must be the case that it must have received F+1 vote messages on something else, on V double prime. Okay, and one of these voters must be an honest party because it's a quorum of size f plus 1, and let us say that honest party is h double prime, and this h double prime would have sent v double prime to h, and h would have observed an equivocation and h would not have committed. Okay? So all of these statements very much rely on the synchrony assumption. So this is for safety within a view. Across views, why can no other value be committed, be proposed? It's because in the same round, if one honest party commits, then f plus 1 of them are locked on it, which is ensured by the notify round. And observe that if some honest party has committed, then there exists no equivocation seen by any other honest party, right? So no equivocating certificate exists. So Byzantine parties cannot have a certificate on any other value. So at the end of the view, that is the only message for which you can have a certificate. So all honest parties have a unique certificate at the end of this view.
You have a question?
I have a short here. So if you see a equivocating certificate, you abort.
If you see an equivocating certificate, no, you don't abort. You just move on to the next view.
In the next view, you have two certificates then.
So in the next view, if you see an equivocation in the next view, you can pick either of them or arbitrarily, because based on this, right? If an equivocating certificate exists, what you can argue is that no one must have committed anything in this view.
This second argument is because the status message needs to contain f plus 1 statuses.
N minus f statuses, yeah. In this case, n minus f is f plus 1. That's right. So if you're thinking of efficiency, you can make it linear if you want, but I guess over here I'm considering the PBFT equivalent. Okay. So if you think about it, with all of these partially synchronous protocols, you talk about these 2f plus 1 sized quorum intersections, right? You say they intersect in one honest party. Over here, that is not what is happening. Over here, a pre-commit quorum of size f plus 1 intersects with a post-commit quorum of size 2f plus 1, where you're sending this message, the certificate to everyone, and this is ensured by your synchrony assumption. Okay, so in that sense, structurally, the way you think about it, reason about it, prove it is different. So another difference with what happens in partial synchrony versus here, over there we always said it's about existentiality. If I have a certificate for something, I know there does not exist a certificate for something else. So over here that is not true. It could be the case that if a leader equivocates, there are two certificates, one for V and one for V prime, and it is not the case that the existence of certificate for one implies the other certificate cannot exist. Okay, and crucially so. All right, so this is a vanilla protocol for Byzantine broadcast. When I'm thinking of it in a single shot setting, you can use the same protocol in a state machine replication setting, where you keep running these 4-round views, over and over again, and you keep committing newer and newer values. Go ahead, Srivatsan.
One question about the previous slide. You can add one more round and make certificates, right?
Yes, I think I will talk about it right at the end of my talk. Yes.
One more round for to compress?
Essentially provability. Yeah. Okay. So you can use the same protocol in the state machine replication setting, where you keep running this protocol over and over again, okay, in multiple views. And in this world, if you have a client request that comes in, somewhere on average in the middle of a view, at some point it will get processed and you'll get a response back, right? And if you think about it, if you have 49% tolerance, and let's assume that these leaders are elected uniformly at random, if that is the case, then you will have an honest leader every 2 views. So in expectation in 2 views, you will get a response. So this would be around 8 rounds, and if you use, depending on what your clock synchronization protocol is, if you're using the NFT protocol, NTP protocol, then this would be 8 rounds is 8 delta time. But if not, you can run a clock synchronization protocol to run these log steps within 16 delta time. So let's go back to the scoreboard. I guess at a high level, what you want, the advantage that you have with synchrony is it tolerates more faults, but you want to ensure that all of the good things that you have in partial synchrony, you can still obtain it in synchrony as well, right? So with synchrony, we showed a protocol which works with lockstep execution, where proposals happen every capital delta time, and where commit latency is ordered capital delta. If you think about it, proposals happening that slow may not be good. I hear from my conversations over here, this view is subjective, but for now I'm assuming that you may want to do it faster. So what you can achieve is non-lockstep synchrony, where you propose at the network speed. Okay, so if your messages are arriving fast enough, then you can propose your next messages faster and faster. Okay, and it turns out that you can adapt this protocol in this work on sync hot stuff and rotating leader sync BFT protocol to obtain non-lockstep synchrony and commit with latency 2 delta plus 2 capital delta plus small delta. So what is the core idea? Again, the leader proposes some value v, all parties receive it, they may receive it at different times, but they vote as soon as they receive this leader's value. Okay, so party 3 receives it first, it votes, and then parties 1 and 2 follow. So we are going to assume that every vote over here also reproposes, sends the proposal to everyone as well. Okay, and now every party waits for 2 delta time after it votes, and if it observes no equivocating message within this 2 delta time, then it can commit. Okay, and as soon as I think even before waiting for this 2 delta time, as soon as a certificate is obtained on this proposal, the leader can propose the next block with the previous block certificate. So this is what allows you to go at network speed. Okay, so the next proposal can happen at network speed. So the question is, why does committing within 2 delta time, why does it suffice? So let's try to reason about it. Okay, so the idea is that if there's no equivocation within this 2 delta time after you vote, you can argue 2 things. One, this value v will be certified, meaning it will receive f plus 1 votes. And second, you can argue that no conflicting value will be certified. So let us see how these two hold from the point of view of some party, let's say party 1. Okay, let's say party 1 votes at time t. Okay, what you can guarantee is that if it votes at time t, within t plus delta, everyone hears a reproposal from this party.
You're leaving the synchronous ROM model here, right?
Yes.
Okay. That's why you
So,
did that, right?
Yes, so I guess we are not going lockstep, but you're still relying on synchrony because you're waiting on this capital delta. So let's think of this from the perspective of party 1. It votes at time t, everyone hears the proposal at time t plus delta. And if there is no equivocation, then everyone would have voted on this value by this time, so it will be certified. Right? So what about anyone else hearing an equivocation and any other certificate forming? Observe that if someone obtains an equivocation after time t plus delta, then they would not vote on this equivocating block because they've already heard about this particular proposal earlier. And what if they have received a proposal, an equivocating proposal earlier? Then observe that they would have sent a reproposal as well, and that would have reached me within my 2 delta time frame, and that would have made me not commit. Okay? In either case, no conflicting value will be certified. Okay? Questions? All right, so proposals can happen every order delta time after you make this change. But commit latency is still 2 capital delta. And the natural question is, is 2 delta like a bound, or can you do better? So generally, as a theoretician, when you see something like 2 delta, you want to ask, why not capital delta? Right? So in fact, when we worked on this, we actually thought 2 delta is a lower bound. Okay? And our reasoning was the following. So in sync hot stuff, if any party votes, all parties detect equivocation. So let's imagine 2 honest parties, H and H prime, where H prime is leading. Okay? It receives proposals faster, and H is lagging. That is, it is receiving a proposal later. Then if H prime votes for a value, okay, it may not reach H until the first delta time, and by then, right at the nick of time, it could be the case that H receives an equivocating proposal that H could vote on, and then we wait until H prime detects this equivocation that H may have received. Right? So you're waiting for 2 things over here: one for this delta lag for H, and one for this delta delay for this B prime to arrive. Right? A natural question is, I think there is this symmetry in equivocation detection. If we can break this symmetry and make it asymmetric, then can we do better? And it turns out that you can. In particular, if only H detects equivocation but H prime does not, then you can actually have a protocol that only relies on 1 capital delta and some small delta terms.
What paper is this?
So I think
What's the full name?
I can share. So I don't know the title of the paper right now. So it talks about good case latency, and this is from disk 20. So it has the title good case latency somewhere in it.
It's all for Byzantine broadcast.
So this, I think the lower bound. So I mean, there are so we have 2 or 3 papers with this. I guess this one we actually showed, if I'm not wrong, an SMR protocol that has this latency. But when you talk about good case latency, yes, it's for Byzantine broadcast.
Question? What can you do if I detect equivocation and somebody else does not? You have to still agree that the leader is wrong before you can propose the next one.
So what we guarantee over here is that if there are 2 proposals, 2 equivocating proposals that happen, then you will know that these equivocations exist. Okay? But what you will guarantee is that if the leading party commits something, then a lagging party would know of it, and for the other equivocating proposal, no honest party will still vote. So you will know of an equivocation. It's a synchronous model, but you will guarantee that up to at most 1 of these values will be committed. Okay, so you can obtain a commit latency of capital delta. Well, you get greedy, right? So you reach capital delta and then you ask, hey, can I do better? Can we commit faster than capital delta time? And of course, someone should shout at me and say, DLS is going to come and haunt you, right? So the latency of protocols tolerating greater than n/3 faults inherently depends on capital delta, right? But then you start asking this question, hey, are we talking about all potential executions? So the DLS bound says, there exist executions where you have to hit this capital delta bound, but there could exist executions where you could be faster. Okay? So if some optimistic conditions hold, then we can commit responsively or at the speed of the network. Okay? So this is something that Pass and Shi had proposed back in their Thunderella work in 2017. So in fact, they had this slow path, fast path paradigm, which said, parties are always either in a slow path or in a fast path at any time. if optimistic conditions hold, then you will be on a fast path and you will have responsive commits. You will commit at the speed of the network with small delta delays. Otherwise, you will do slow commits. Okay? And they had this detection algorithm where you will be on the fast path. If you don't make progress, you will have a transition phase, and then you will move to the slow path, and then you will again test these conditions, right? So it required parties to guess and test conditions, and if you have incorrect guesses, then you would have bad latency. So the natural question to ask is, can you actually do better? Can you obtain good latency, and in fact, can you obtain some sort of an optimal latency? And it turns out that, if you're tolerating more than n over 3 faults, and let's say your optimistic rule tolerates at least one fault, then you can argue that the sum of latencies of your optimistic commit rule and your synchronous commit rule will be at least 2 delta. Okay? So in particular, you can show that if a protocol pi under one fault, if it has alpha latency, under f faults if it has gamma latency, then you combine, you add up alpha and gamma, and if it turns out to be less than 2 delta, then you can show that this protocol is not secure. There exists an execution where agreement breaks. Okay? So in particular in world 1, in the optimistic case, if you obtain alpha latency, in world 2, under f faults you obtain gamma latency, then there exists a world 3 where the protocol has to break if alpha plus gamma is less than 2 delta. And based off of this, we actually showed 2 protocols. One which said, in the optimistic case, you will have 2 small delta latency. Okay, small delta is the actual network delay, and in the synchronous case, that is when you have f faults, you will have 2 capital delta latency. Okay, so the sum of them, ignoring the small delta terms, is 2 capital delta. Okay, and the optimistic condition over here is greater than 3n over 4. Okay, so if you have 76% corruption, if you have 76% honest parties or less than 25% corruption, that is when this can hold. Okay, so the intuition behind 75% or 76% over here is, 2 76% will intersect at one honest party when your overall corruption threshold is 49%. Okay, so this is the same intuition at some level with what Ethereum is implementing with these fast confirmations with FCR, okay, where they have the 75%, if you have 75% votes among all of the validator sets, and if synchrony holds, they say you can fast confirm right now. And it would be the case that, when something gets finalized so far as synchrony holds, then the same value will be finalized. Okay, so the finality, the backend over there is different. It's a partially synchronous protocol. Over here, it's a synchronous protocol, but for the particular commit rule, it's the same idea. And recall that over here we said this condition holds only when this optimistic rule tolerates at least one fault. Well, what if the optimistic rule does not tolerate any fault? Okay, so the level of optimism is one where everyone is honest. At that point, you in the responsive case you can get 2 delta latency, but in the synchronous case you can actually do much better. You can achieve this capital delta latency.
Sorry, what's the size of the certificate you need for this responsive latency?
So over here it's 76%. Here it's all 100%.
Okay, the certificates are n, and
exactly.
so the certificate is much bigger.
Exactly. Okay. All right. So in our comparison, you can obtain a commit latency of capital delta. Optimistically, you can make it 2 small delta, but that makes your latency 2 capital delta in other cases, okay, in the synchronous case. And the optimistic condition over here is f less than n over 4. So you heard of a couple of talks from a couple of days ago which spoke about the corresponding versions in partial synchrony, where you have commit latency that is 3 small delta time, and optimistically you can do 2 small delta latency. Over there, the optimistic condition was f less than n over 5. Okay. Until now, right? If you look at everything until this portion of the slide. Everything looks green and nice in the synchronous part, except for the first one, I think which I said you should remember. This is an assumption we are making, and it's a strong assumption that you're making. Every message will respect synchrony. So for the most part, it is true, but until it is not, right? And if you're running a long running system, it can break at some point. So can we get rid of it entirely? Then you'll move to partial synchrony, right? So you're trying to somehow balance where you want to still live in the synchronous land because you want to tolerate more than n/3 faults, and yet you want to allow for some degree of asynchrony. So the question is, what if the synchronous assumption breaks? Can we think of models where we can weaken the synchrony assumption and yet get something nice? So I'm going to discuss two different models over here. The first one is what we call the mobile sluggish synchronous model. So this was originally proposed by Guo, Pass, and Shi in 2019. Okay, and the intuition over here is something that I guess Patrick mentioned sometime earlier in his talk today. Alberto mentioned about it yesterday, where you just have some temporary loss of connection for one node, right? My AWS is throttling my network, or for some reason I'm not able to send these messages right now. Okay, so when this happens, I'm going to call myself sluggish. Okay, so some parties can be sluggish because of a temporary loss of connection, but over a period of time, at some point they will recover and they will be prompt again. But the more important thing is, if you run the protocol long enough, then this failure that happens to you can happen to someone else as well. And over a long period of time, all parties can be sluggish. Okay? So if I have sluggish parties, can my earlier analysis or can these earlier protocols tolerate anything? At the very least, I would say, at least some of the statements I made, would trivially break. As an example, over here we said from the perspective of party 1, if it at time t, if it votes, everyone would hear the reproposal by time t plus delta, and this was required for ensuring both this value v will be certified and the fact that no conflicting value will be certified. If this party 1 is sluggish, that no longer holds, right? So your commits can break at least with the protocols that we have described. How bad the break is, I think let's not get into that, but at least the analysis that we made will no longer hold true. And in particular, if a large fraction of parties are sluggish at any time, at some level you're going back to this DLS bound. If you have 40% Byzantine parties and 35% malicious parties at once, then you cannot do much. So we are trying to look at some sort of a middle ground over here, and the assumption that we make over here is that at any point in time, you have a majority of honest parties who are honest and prompt. Okay, prompt meaning not sluggish, and others can be sluggish. So an interesting way of thinking about it, an interesting setting to think about is, you're tolerating 40% Byzantine faults, okay, and 9% of the parties are experiencing these connection losses. Okay, they're losing synchrony, and the remaining 51% are honest. And as time progresses, the 40% stays fixed, they are static, but the 9% can switch among the remaining 60% in such a way that at any time you still have 51% prompt parties. So if that happens, what can you do? Let us say over here party 1 is sluggish. How can you deal with such a sluggish party? The problem is, if it sends a message to someone, no one may hear of it, right? So it sends a vote, this vote message, because it's sluggish, no one gets it. The idea is there are several honest and prompt parties. You use them indirectly to communicate with everyone else. Okay. In particular, let us say any party, if it hears f plus 1 reproposals and then it votes, then what is guaranteed is that among these f plus 1, at least one party is prompt. And if I am hearing something from f plus 1 parties, one of them should be prompt, and that party would send this reproposal to everyone else. Okay? And whatever task I was doing in this proof, will be done by that prompt party for me. So I'm using these prompt parties as an indirect communication channel. And it turns out by just using this idea, you can basically just add one additional responsive round of voting, which adds order small delta terms to your latency, and you can deal with these mobile sluggish parties. So we originally showed this for sync hot stuff, but then we said, for most synchronous protocols, you can just apply the same idea and it just works. So this is one model. Over here, you're thinking of every party as being as losing connections or having connections. So when it is prompt, it is able to reach all prompt parties at any point in time. A different model is a new notion that we came up with a couple of years ago called granular synchrony. So over here you're making timing assumptions, but you're making these timing assumptions based on the links that are there in this connection graph. So consider a graph where nodes are parties and edges are connections between them. Okay? For every edge, you will label them as synchronous or partially synchronous, or for that matter asynchronous. Okay? If all of these links are synchronous, then that's the synchronous network model. If all of these links are partially synchronous, then that's the partially synchronous network model. And if some links are synchronous and some links are partially synchronous, you get a model that is intermediate between synchrony and partial synchrony. And it turns out that this model allows us to tolerate somewhere between n over 2 and n over 3 faults. Okay? So in fact, in this work, we showed a necessary and sufficient condition that needs to hold for a graph for consensus to be solvable in this graph. Okay? So we showed that consensus is solvable if for all honest sets, all honest vertices, vertex sets A of size at least n minus 2f, it is the case that there exists an honest set size B of size at least f plus 1 in such a way that A can reach B. Okay? If you're looking at this for the first time, I don't think this statement would have made sense. So let's try to step through. Again, we are going back to this, this diagram that you have. Let's say you have over here, I'm denoting by X malicious parties. There are synchronous links between X and A. Go ahead.
Sorry, did you change the underlying graph, or are you just saying that some links go down in the clique?
So you have a clique, and for every edge, I'm labeling them either synchronous or partially synchronous. So and that stays fixed.
Are they mobile also? They can change or not?
So over here, we don't consider mobile faults, and so we assume it's static. But answering this question for mobile is it is an open question. It's an interesting question.
Deriving from the previous talk, can we kind of assume the X partial synchrony model?
As somewhat of an intermediate model? You could, so far as you can argue that you can tolerate more than n over 3 faults, right? So over there, at least if I understand it right, you're still tolerating only n over 2, only n over 3 faults. So whenever I want to do any of this, so whenever I want to make a synchrony assumption, I think my goal is to be able to tolerate more than n over 3 faults. Otherwise, I can just rely on partial synchrony.
The X partial synchrony is 7.
It is n over 2? Okay, then that is another model that we can consider. I see.
isn't it like you need n over 3 for liveness, but in detect n over 3?
Compatibility.
Sure.
Yeah, compatibility.
Yeah.
I see. So in that case, yes, I think it is another intermediate model that one can.
Not actually liveness in n over 3, so it's incomparable guarantees.
You won't be safe, right, in these periods of asynchronous.
Okay, I mean, for now, I think I'll go on with granular synchrony. So remember this diagram where you have X, which are Byzantine parties. They have links to sets A and C, both of which are two separate sets which have partially synchronous links in between them. That is, they may not be able to communicate with each other until GST. So if X is of size f, and if your set A is of size at least n minus 2f, and let's say C is of size less than n minus 2f, then what we are arguing over here is that if A makes, what we are arguing is that if A union X makes some progress in the protocol, then it must be the case that A should be able to inform at least some larger set B of size at least f plus 1, so that consensus is solvable. So think about it in the following way. So what you need is, in the context of simplex, if you have a commit certificate, you create this commit certificate of size n minus f, right? So out of those n minus f of them are malicious. Okay, you have n minus 2f that remain. And when you're thinking of a world where f is greater than equal to n over 3, at that point you cannot argue that this n minus 2f honest will intersect with any n minus f at least one honest party. But if it is the case that whatever this set of n minus 2f, whatever it is that they do, if they have synchronous links with a larger set B of size at least f plus 1, then you have some sort of a guarantee that a larger set knows about it, and this f plus 1 honest parties will intersect with any n minus f at least one honest party. So again, the condition that we have is that if you have for all honest sets of size at least n minus 2f, there exists an honest set B of size at least f plus 1 in such a way that A can reach B. And what exactly do I mean by A can reach B? If a message arrives at all parties of A, then within a bounded delay, it will arrive at all parties of B as well. Okay? So this is not saying that all parties in A are synchronous or all parties in B are synchronous. That is not true. All this says is that for every party in B, there exists some party in A who can inform it within delta time, that there is a synchronous link in between them.
But it should delta S.
Sorry?
So it should delta the total delta here. I mean, if a message arrives at all parties of A and arrives at all parties of B, in the worst case you need two deltas to guarantee that.
Yes, I think you will have to wait for delta time for A to inform B.
This could be like n times delta, right?
Yeah, I think I'm kind of so far as there is so the way I think of it is, if there is a link between A and B, it could be a line, and at that point it could be n delta as well. So n delta, I'm thinking of it as a larger big delta. It is a synchronous link. So that does not affect this necessary and sufficient condition, that affects perhaps performance. So an interesting aside that I want to bring up is, so we had this model, and then there was this paper that came up, you may have heard of it, it was called Alpenglow. And they made this interesting claim of 20 plus 20 tolerance. Okay? And what we realized is soon enough that it is actually not achievable under partial synchrony. So by the way, what 20 plus 20 meant, you can tolerate 20% Byzantine and 20% crash fault simultaneously. So what we learned is that you actually cannot achieve it under partial synchrony, but the paper actually relies on a combination of partial synchrony and what they call assumption 3. Okay? And assumption 3 basically says, when the proposer is proposing a block, if one party delivers a block, other parties cannot deliver a different block. Okay? And the protocol basically says your proposer, when it is proposing a block, it sends erasure coded shares of the block to parties. Each party, when they receive these erasure coded shares, they will send these shares to all other parties. Okay? And when I receive sufficiently many shares corresponding to the block, at that point I will reconstruct the block, and if I observe no equivocation, that is when I am going to vote. So pictorially, if there is a proposer, it's proposing a block B to these parties, each one will receive a share, S1B, S2B, and so on and so forth. These parties will broadcast these shares to everyone, and everyone will reconstruct the block over here. Okay? And they will vote if they do not observe any equivocation. So a malicious proposer could send two different blocks, B and B prime, and in this case what would happen in what they claim is that this party over here, it will vote only if it does not learn about any share of B. Okay? So it is able to reconstruct everything for B prime, but it is not able to hear about any share of B. And if you think about it, what this is saying is that for this particular party, it must be the case that it hears nothing from any of these other parties, and that is when things can go wrong and it would vote. In other words, if there is at least one synchronous link between this party and one of these parties, then this would not happen. Okay? And similarly for all of these parties. So you can think of this world as there being a granular synchrony model where some of these links should be synchronous, but the rest of them could be partially synchronous. Okay? And this, so in a sense, they're using granular synchrony to actually reduce their to actually improve their fault tolerance.
Can we generalize? Because in the 90s there were a lot of papers that say that if you receive all the messages in malware, you can decide fast. This is a form of synchrony, right? So any assumption that you're making the order at which process deliver? Because here you can deliver all of the left and none of the right, then all of the right, right?
Yeah, I think I'm.
First the left, then.
So yeah, I think over here when we say synchrony, we are saying we will wait for delta time and we will hear. That is kind of not what they do. They kind of say if I receive all of these first and then I receive them, I think so. It is a little different in that sense, but I guess a slightly modified version of their protocol can be easily analyzed in this granular synchrony model.
In the paper we cite these. Yeah, these papers we cite these and compare and look at the crash failed fault plotting. How we can do that.
Okay, so the last aspect that I would talk about. So how much time do I have?
15 minutes.
Okay, good. So the last aspect that I would talk about is on provability. Okay, so again going back to what we were talking about with partial synchrony protocols, we said if a commit certificate exists for a value, it cannot exist for an equivocating value. Okay, so in a sense you can use these certificates as provable certificates where I can show it to Kushal, and Kushal would be happy. He'll look at the certificate even if he does not know anything about the protocol, but he would know that this has been committed. And as is for the kind of certificates that we have been talking about in synchrony, this has not been true. Okay, in particular this example that I'm showing you here for the second time, you can have certificates for both V and V prime. Okay. So in this recent work, we talk about provability as being a first class citizen, where the simple idea is what Srivatsan mentioned. You can just add another round of votes, right? So right now with synchrony, when I commit something, I know I have committed, but I cannot prove it to an external party. But if f plus 1 honest parties do that, then out of f plus 1, f could be Byzantine, one of them is honest, So if f plus 1 parties tell me that I have committed, then that effectively says that it has been committed. Okay. The problem though is that this worsens good case latency from 2 rounds to 3 rounds, and ideally we don't want to do that. So what we consider is in this world we ask if provable certificates are a first class citizen, then can we have fast paths where you can have where you have again provable certificates but you commit sooner in 2 delta time. Okay? And in particular what we show is that if you have a setting with n equals 2f plus 2p plus c plus 1 where f is the number of Byzantine faults, c is the number of crash faults, then one of the protocols that we show is a lockstep rotating leader protocol, where you have a commit certificate that is formed within 3 delta time. It's a provable commit certificate that is formed within 3 delta time, and you have a fast path of 2 delta time when f is less than equal to p. So this f less than equal to p optimistic case is very much similar to Fab, SBFT, Alpenglow, Kudzu, and so on.
Sorry, what's P?
So P is the optimistic fault tolerance. So
you can create a certificate that has more than n minus f by p.
Yeah, I think so. Think of it as a certificate that is created with n minus p, for example. Yeah. So in the general case, you will only obtain n minus f minus c, but over here, if you can get it with n minus p, where n minus p is a larger number, then you have a fast path.
But in practice, you wait a little longer to receive this p additional, or
sure. Yeah, I think that's the same trade-off that you have in partially synchronous protocols. Yes. So this is one protocol. We have 3 other variants which talk about this is in the lockstep setting. We have other protocols that talk about responsive views. We have simplex variants as well in our paper, and we also have a lower bound that relates this fault threshold and support for fast path with less than 3 delta time. All right, that's my tutorial. Do you guys have any questions? So here are some of the references that we for some of the papers that I spoke about. Go ahead, Akhil.
Is there a difference between mobile sluggish format and the sleepy format?
Yes, they are different. So in the sleepy model, what you expect is that it can be the case that 90% of the parties go offline, and the remaining 10% parties have to still make progress. Right? In the mobile sluggish model, we do not allow that. We require 51% of the overall parties to be awake and online and prompt at the same time. So in that sense, they are very different.
And one more question I had. You said proposals every small delta time, right? Why can't this leader just keep proposing continuously?
You can. So what you can do is, I can propose for 5 slots at once, right? So the typical reason why you would want to do something like this, especially in a rotating leader setting, is that if the content of what I'm proposing depends on the previous content, then you would want to wait until I know something about the previous content, and that is where this dependency comes in. Otherwise, I can trivially just submit 5 or 100 submit proposals for 100 slots at a time, and in fact I can think of all of these proposals as just one mega block. Right?
We have this, you did talk about this paper where we do this rotating leader.
I think I did not. Yeah, I think we do it, but I think we did not talk about. So I did not touch upon that paper.
Because these 2 delta protocols, right? They actually commit in the background. So it's actually you're not paying it on the critical path.
Yeah.
It's kind of critical.
Sync hot stuff already had this probability, right? So what's different? What's the
Very hard stuff is not, the certificate is not provable.
Or I guess the paper already had these mentioned somewhere that you can add this.
No, I mean I don't. I mean not that I'm aware of.
Is there a way of that you make here in the 2026 paper?
So I guess the key trade-off that comes up is, as soon as you say I want provability, you incur one additional delta, and at that point you start asking, can I get better latency? Because otherwise, you can take any synchronous protocol, just add one round of votes, and that gives you provability.
Or I guess what I meant by saying hot stuff added is like, in some sense, to support mobile sluggish faults, what you're doing is basically proving it to those.
But you're proving it to these sluggish parties. You're not proving it to an external world.
Is it different?
So if some party commits, then that's still local, right?
So if a party is sluggish, then it doesn't have any of these timing information about it. Did I see equivocations and time? So basically how you're telling the sluggish party that something was committed is by giving it a provable certificate, right, of F+1 votes after committing.
But what an...
Is that the same as provability, or is that something?
No, I think what can happen though is that a certificate could lurk in the wild. So generally, I guess with provability, here's the dilemma, right? So what can happen is that Byzantine parties can vote on something, and I can take one vote from someone else, and I can create a certificate in the wild that no one knows about. But I think maybe what you're saying is that with mobile sluggish, you already have this one round of votes. So maybe that's true, but I think I'll have to think about it and verify.
I was thinking of it as exactly the same thing as.
I see. Let me think about that. That's a good point.
I think about sluggish as crash. It's the same as about crash.
So I guess you can think of it as a mobile crash that is guaranteed to recover, not guaranteed to recover. So I guess if it crashes. So the requirement that you have for sluggish parties is that once I recover, then I would receive all of these messages over the network. So if your crash parties, once it recovers, if it can retrieve these messages, within some amount of time, then I guess that is reasonable.
Yeah, very good tutorial. There are two things. The first is a general question asked for people from the Synchronous Byzantine. There was in the real-time community in the 90s something like semi-synchronous model, that some links are synchronous and some links are asynchronous. I don't know if you are aware of in the relation of this with the last work, which is when you have some links that are synchronous or that are asynchronous.
So I think, as far as I'm aware, the semi-synchronous model basically said you have some sort of a distribution over these links, no? I see. I think then I'm actually not aware of it.
We cite them, right? I said we cite them.
That's from the Portuguese.
Yes.
From what the Portuguese. Yeah, okay. And the second question is luggage. I never really understood. So as luggage, the message of this luggage can be arbitrarily delayed, or this luggage can take longer to receive message from other processes?
Both.
Both.
Yeah. So if I'm sluggish, I may not
receive everything that was.
Yes.
So you are kind of assuming that the synchrony is like false, they are uncorrelated. So the fact that one group is asynchronous or not synchronous do not affect the operation of the rest of the network.
Yeah, I think that the precise definition of a prompt party is that if a party is prompt at some time t1, then the message that it sends will arrive at any party at time any prompt party who is prompt at time t2, where t2 is greater than or equal to t1 plus delta. So what that means is that if at some point, at T1 plus delta, if someone is sluggish, they will not receive it. But when they become prompt, let's say 10 delta later, at that point they will receive it, because that would be their T2 when they are prompt.
And my question is in general, is other people using this sluggish market? I know this sluggish market for 4 years, but I don't see a lot of follow-up.
So in general, I think from my understanding, I guess, for this entire area, I guess with synchronous protocols, I think a nice thing is you can tolerate more faults. But practitioners, as far as I understand, I think they're still hesitant to use it, because you're relating safety to the synchrony assumption. So the two interesting examples that I have been excited about in the past year has been Ethereum's FCR, and the fact that it has been used in some sort of a nice way in Alpenglow to improve fault tolerance bounds.
So in MPC related distributed cryptography related literature like Anil, they assume broadcast time, and for that that is not Byzantine broadcast, right? Like you need to elect an honest leader for that, and then you have to make sure that honest leader comes. So what's the expected latency for that?
So I think, as far as I'm aware, I guess for most of the literature in MPC, so whenever you broadcast, you kind of just multicast it to everyone, and you assume that you would do it correctly, and that is what most protocols assume. And so I think there are some works which talk about connecting these works, and I guess some of the people who work on it are actually Aniket, and maybe Itai has a couple of papers on this topic.
I think a lot of, if you look at these papers, a lot of them actually show how with a little bit more effort you can get a constant expected number of rounds for the active adversary. Kartik was showing basically, SMR that blockchains like. But simpler variations of this give you constant expected number of rounds for the active adversary.
Because I don't know about the redundancy, at least peptides capital.
Deterministic, that's why I was saying expected constant.
Mr. Kartik?
Thank you.